So here we consider the cooling energy savings with co-roofs. And to do this, we analyzed 17 buildings, some pre-existing, pre-code, and some after the introduction of the National Construction Code, both low-rise and high-rise, some also mid-rise, of different categories, including offices, retail, houses, apartment buildings, as is mentioned, considering the architects from previous work of the department. For all of them, we considered a version of the same building with a roof albedo of 15% and one with a co-roof with albedo of 85%. For all of them, we had like no wall insulation and minimal roof insulation, like an anti-cold blanket for pre-code buildings, and for new buildings, the NCC 2019 DTS levels, depending on the climate zone. For all of them, we consider occupancy profiles and internal heat gains following the NCC or NATHERS for residential buildings, which are pretty much in line with the values given by ASHRAE. And we performed simulations using Energy Plus as a simulation engine, perhaps the most validated simulation environments for buildings, considering the HVAC in operation, and the free floating conditions, so no air conditioning or heating. And for when the HVAC is operation, we consider a set point for heating of 20 degrees and cooling of 25 degrees, and an ideal HVAC, namely we were computing the heating and cooling loads. With these settings, we use two weather data sets, one coming out of the climate modeling, considering only January and February 2017 for the unmitigated and mitigated scenario, and then all year simulations only in the unmitigated scenario, because of course we don't have access to a parallel reality where roofs are spread all across Sydney, and we use data from the Bureau of Meteorology, and we use a single year from including the summer 16-17, because it includes several heat waves, but it's not the maximum, it's not an extreme situation. And we couldn't use a typical reference here because we were also considering the simulations performed with WRF. For Sydney, we used 11 stations, Melbourne 7, Adelaide, and Perth 5. And in all these cases, we took stations that were on the coastal, in the coastal regions of the city, inland, in and out of the main urban area, to offer an appraisal of the whole of the different climatic situations that you might encounter in the different urban settings. The results, so let's take a look at uninsulated low-rise office buildings. If we have such a building in Richmond, we have a cooling load of approximately 29% here, while along the coast, the same building would have a cooling load of 22%, so considerably lower. When we put a co-roof in the same climate conditions, so without any mitigation, we have to change the scale of the chart because otherwise it becomes all flat. And therefore, the low part of the scale of the black roof, it becomes the top of the scale of the co-roof. So here in Richmond, the same building with a co-roof would have a cooling load of 21-22 kilowatt-hour per square meter over those 2 summer months. And then along the coast with a co-roof and also a co-roof climate, namely all the buildings in Sydney have co-roofs. In that case, we have the cooling loads as low as 10 kilowatt-hours per square meter per Kelvin, or something in the neighborhood of 15 in Richmond, so considerably decreased. This is again, so let's take a look at the relative savings. So with only the co-roof on the target building, we achieve between 22 and 26% cooling load savings. When we have the widespread application of co-roofs all over Sydney, we can have savings ranging between 38 and 54%. And the important thing is that these savings are considerable in the hottest portions of the city. So both in relevant parts, in relative terms, but also in absolute values. Then we might say, okay, this is for a low-rise office building. There might be a heating load penalty. There is, but it's contained, and it's of the order of magnitude of 1%. When we are considering a one-year simulation, not just for the summer months. And in the end, we still end up with a benefit on the final balance. So with a total thermal load savings in the range between 18 and 23%. This was for a low-rise building, but what about a high-rise building? High-rise building, only a small portion is the rooftop. Only the top floor will feel the benefits of the cool roof. The bottom floors maybe not that much, and indeed the benefits in this case, they are in the ballpark of 5%. But when we are applying cool roofs all over Sydney, in that case, the air that flows into the building while opening the window or taking in from the air handling unit, it's cooler, and therefore we are saving a lot of energy and ending up with significant savings also for high-rise buildings. Likewise, for insulated buildings, we might say, okay, if we have a high-rise insulated building, again, the benefits will not be huge, and because it's insulated, so therefore the exterior surface temperature will not play a huge role on the thermal balance of the building, and indeed the savings are contained to 1%, as it's unsurprising. However, again, when we have a widespread application of cool roofs all over Sydney, the savings are significant, are remarkable, because we are bringing in air that doesn't need to be cooled as much as in the unmitigated scenario. This was for office buildings, for commercial buildings. Let's take a look at residential buildings, houses in this case, and whether we build our house here in Observatory Hill in the Darling Harbour, and we're very wealthy, or here in Oxbury in Richmond. And here we see that without air conditioning, the indoor air temperature would be as high, with a black roof, as high as 42 degrees for a new house. While with a cool roof, we can substantially decrease the air temperature indoors by as much as 3.84 degrees. So it's a life-saving reduction in indoor air temperature, exactly where we need it the most in the hottest portions of the Greater Sydney area. And reducing also the number of hours when we need the air conditioning. So from 456 to 356 hours, so 100 hours less during a typical summer month. During winter time, also we have a reduction in air temperature. Yes, this reduction is not as big, as not like a 4 degrees reduction as we were seeing before. And indeed, it has a limited impact on the thermal balance because the heating penalty for houses is between 0.7 and 1.7. With a total thermal load savings, again, in the range between 10 and 19%, considering all stations. You might have thought, okay, these are simulations, so you guys messed up with the simulations. What about real world? That this is as real as it gets. We, in the past project, we deployed sensors in 106 buildings all across New South Wales, mostly in Sydney, and we measured indoor air temperatures as high as 40 degrees, and in other cases as low as 8 degrees. In this case, it gets to 12. And look, what's the situation for this this house? Look at the solar absorbance of this rooftop. Another good reason to minimize the cooling loads in buildings is that during heat waves, the electricity demand peaks, so we risk having blackouts and brownouts, and an increasing frequency of the times when the transaction reach the cap, and therefore increasing prices of electricity. So again, important to reduce the peak load due to air conditioning. So to sum it up, roofs can save energy, especially when applied onto a single building, even when applied onto a single building, and the most significant savings are achieved with a regional application. So when roofs are applied onto all buildings, the cooling energy savings are significant, even for high-rise and even for highly insulated buildings. So it's important to have it in all conditions. There are heating penalties, however, they're modest. So they are maximum 2% in our climate context. And then in the future, with climate change and increasing urban overheating due to urbanization, those heating penalties will vanish, will be even smaller. And especially during heat waves, roofs and houses can reduce the indoor air temperatures by more than 4 degrees. So they can be life-saving. So if you have a further curiosity for a single situation, at the end of the project, we will publish one brochure per building for each city. So well, you will have the detail for all the results. Thank you for your attention.